Hello, in this presentation I'll be presenting SOAP, a cross-sensor domain adaptation technique for 3D object detection using stationary object aggregation pseudo-labeling. State-of-the-art LiDAR-based 3D object detectors all use deep neural networks and supervised learning. This naturally requires a large amount of labeled data, but more importantly, when applied to a different domain, such as point clouds collected by a different sensor configuration, the object detectors often experience a large performance degradation. For example, comparing the performance of a state-of-the-art object detector VoxelNext in cross-sensor setting and in-domain setting, we can see a very large performance gap. And in this work, we aim to address this problem when switching to a different sensor. In particular, we consider the cross-sensor domain adaptation problem, where we're given a object detector trained on labeled point clouds collected using one particular sensor, which we will call the source domain, and we want to improve the detector's performance on the point clouds collected using a different sensor, which we will call the target domain. And further, we will assume that either no label, meaning the approach is going to be unsupervised, or only a small number of labels, or semi-supervised from the target domain is going to be available for us. Our method is based on a key observation that the sparse point clouds collected using different LiDAR sensors have very different scanline patterns. For example, when looking at a sparse point cloud from the nuisance dataset, which is collected using 32 beam LiDAR, comparing that to a Waymo point cloud collected using a 64 beam LiDAR, we can see a very large visual difference. And more importantly, when we look at the Z component by plotting the CDF of the Z location for each point, we can see the distribution between the nuisance point cloud and the Waymo point cloud is very different. However, when aggregating more frames, then that difference between the scan patterns is going to become smaller, as demonstrated here by the visualization of the point clouds as well as the CDF plot. For stationary objects in particular, aggregation also provides a more complete geometry for those objects. So this inspires us to design a domain adaptation method that utilizes aggregation technique. In summary, our technique is motivated by, first, aggregation improves the representation of object point clouds by densifying them. And the scanline patterns I mentioned in the previous slide can be reduced by aggregating more frames up to full sequence aggregation. And that stationary object can benefit the most from the full sequence aggregation. So our main idea is to improve the cross-sensor pseudo-labels, in particular the stationary objects, by exploiting the scene-level full sequence aggregation to try to close the domain gap that's caused by the scanline pattern difference. As a first step, we propose to use scene-level full sequence aggregation, where the individual point clouds are aligned in the global frame using equipose and concatenated together. An example of the aggregated point cloud from this process is shown on the screen. As we can see, for stationary objects, they are densified with a more complete and more accurate geometry. However, for dynamic objects, because due to their motion, the point clouds tend to be distorted. In the next step, we want to use this full sequence aggregated point cloud to train a detector to detect those stationary objects using a technique we call the quasi-stationary training. And this is to solve the problem with what we call a quasi-stationary objects. So a quasi-stationary object, as we define it, is an object where it is not strictly stationary, so it can be moving, but after aggregation, the point cloud will have very little distortion as if the object is stationary the entire sequence. We propose a technique called quasi-stationary score to identify those objects, and also a technique to construct consistent training targets for those objects during training. Our results show that it can improve the training stability and also the performance for those stationary objects compared to a naive filtering based on speed or based on object motion. Next, after generating the predictions from the full sequence object detector, we propose a post-processing technique called spatial consistency post-processing, which we exploit the stationarity of the detected objects by using clustering and filtering in the global coordinate system to make the detection more consistent. The refined pseudo-labels for stationary objects can then be combined with a pre-trained detector so that we also recover the pseudo-labels for the dynamic objects using a weighted box fusion. The final pseudo-labels can then be used in different domain adaptation technique such as fine-tuning or ST3D, SSDA3D, and so on. Our evaluation showed that SOAP can improve over the baseline and close a large amount of domain gap. More interestingly, the faraway objects, for example between 30 and 50 meters, receive more improvements compared to close-range objects. This highlights the benefit of using full sequence aggregation in this context. This is also evident by the qualitative examples where from the highlighted region, we can see that SOAP can identify those objects that are far away or occluded that otherwise are completely missed by the naive pseudo-labeling approach. Furthermore, SOAP can complement other state-of-the-art techniques such as ST3D in the unsupervised domain adaptation setting, where we see a huge improvement by combining ST3D with SOAP. And in the semi-supervised domain adaptation setting, when combined with SSDA3D, we also see a large performance improvement in terms of both AP and domain gap closed. In conclusion, our proposed SOAP can effectively utilize full sequence aggregation to generate high-quality pseudo-labels for cross-sensor domain adaptation. Our method can also complement other state-of-the-art techniques such as ST3D or SSDA3D, improving their already impressive results. As a future work, we would like to explore the benefits of introducing a tracking or second-stage refinement component into our pipeline, and also exploring other synergies with other state-of-the-art approaches. Thank you.